We're working on chapter 13, probability, yesterday, and I apologize for this not getting recorded. Yesterday we talked about sample space. We showed how to do a tree diagram, how to use that to create an organized list, and how to use the tree diagram to make a table. Hence, it's exactly like the tree diagram. It just looks like a table. Yes, ma'am?
You only turn the skill practice, right?
We're going to do both. No, the study guide and skill practice.
So we have to turn both of them.
You have to turn both. That's why they're stapled together. Then we also talked about the fundamental counting principle, whereas basically the total number of outcomes is, hi, I'm just going to multiply all the different options together. Okay? And that's going to give me my total number of possibilities. Start with section 13.2. We're talking about permutations and yes. We're recording too, so thank you. Probability, we're going to start with permutation and combination. Permutation is when we're arranging objects and they have to be in a specific order. Like books in a library have to be in alphabetical order. To find the number of permutations of objects, we're going to end up using this new number thing. Here's our new number symbol. We've decided to add punctuation to our numbers, not just letters. And so now we have an exclamation point. As if algebra wasn't weird enough. This exclamation point stands for the word factorial and is a countdown with multiplication. So if we're going to start with 5 factorial, we're going to count down and multiply as we count down. So 5 times 4 times 3 times 2 times 1. Big explosion because the world ends. So you can do that on your calculator. Grab your calculators, do 5 factorial, 5 times 4 times 3 times 2 times 1. Hit enter to make the world blow up. And that's 5 factorial, 120. Okay. Then you can have it be Happy New Year for you. The thing is while this is well and good, imagine trying to do 99 bottles of root beer on the wall factorial. 99 times 98 times 97. Are you already bored of hitting the multiplication button?
No.
Yes.
Yeah, and I've already messed up somehow. So there has to be a shortcut. These calculators do indeed have the shortcut, so please type 99, and then we're going to slide down to the very bottom of our calculators, right by the G button. You'll find a button that has a question mark and an exclamation point. This is what I like to refer to as the button. Push the button and scroll over to the exclamation point.
It gives you 120.
Okay? So 99 factorial is that number. Okay, but wait, do you see the little triangle here? That means that the number actually goes off the screen. So if you scroll up once and then push to the right, you're going to get to the end of the number. And then you can hold down the left key and see just how big this number is.
It's a big number.
Oh my God.
It's not that big if you guys think about it.
It's certainly not bigger than, say, 1,000 factorial, which is likely way bigger than this.
Yes, I'm still scrolling.
Yeah, me too. So this is why instead of writing this big mess, we're going to write 99 factorial. Okay? These formulas make use of this countdown multiplication, factorial, in order to make them work. This symbol, lowercase n, capital P, lowercase r, is our permutation formula. We're going to use permutation anytime we have some number of distinct individual objects that we're putting in order and we're taking them a certain amount of objects at a time. Okay? Let's look at question number 1 so that we can see that in action rather. So number 1 says we have textbooks for each one of these different classes: Spanish, English, chemistry, geometry, and history. 6 different classes, 6 different textbooks. We're going to choose 4 of these at random to put on our bookshelf in our locker because our locker is narrow and lame and doesn't have room for all 6 textbooks. The other 2 we're going to throw in our backpack and not worry about them. We want to know what's the probability that when we selected these textbooks, we end up with the geometry and the chemistry in that order, and then the other textbooks in whatever order they want to be in. we have to find 2 bits of information. We need to find out the number of outcomes that we're looking for. So the number of outcomes we want. And then we want to know the total possible outcomes. Let's look at the total possible outcomes first. We have 6 different textbooks from which we can choose 4. And since order matters, this is a permutation. So this is 6 permute 4. The formula for that says n, which is the number that came first, factorial, divided by n minus r, that result factorial. You can put this in your calculator straight as it is, but I'm going to simplify in parentheses here. 6 minus 4 becomes 2. So I want to know what is 6 factorial divided by 2 factorial. 360? The factorial button is the button down by the G. It's the button that has the question mark and the exclamation point next to it. It's this button, baby. This one right here. Yeah. The button.
I found it myself.
You found it. Good job. So 360. So there's a total possible outcomes of 360. Now we want, this is total. Now we want to know how many possibilities are left for these 2 positions. After we've selected geometry and chemistry, how many textbooks total are there for us to choose from? Say it. The first number you were going to say.
4.
4. Because we had 6 textbooks total. We've already selected 2. We have 4 left that we can choose from. How many positions do we have that we can put these 4 in?
2.
We have 2 positions left on our bookshelf, which means this is, once again, another permutation. This time, we have 4 permute 2. Using the same formula, we end up with 4 factorial over 4 minus 2 factorial. Please use your calculators and tell me how many choices we have for this one.
Green.
4.
Calculator battery ran out.
It ran out?
Yeah.
Uh-oh. Do you want to trade?
No, I was just kidding.
Okay. Because Angel Romanoff never lets me down.
4 minus 2.
12.
12. So the probability that if we did this completely at random, we put our books in our backpack, is 12 out of 360. So if we did this 360 times to get all the possible combinations, 12 of those would end up with chemistry first, or geometry first, and then chemistry. Reduce this fraction. Use your calculators.
1 over 36.
30. Close. 1 over 30. Now use your calculators to turn this into a decimal. 0.03, and then the 3's are going to repeat, so we're just going to chop it off right there. Now use your calculators to turn this into a percent by multiplying this decimal by 100. 0.3 or 3? 3%.
Because you move it.
You didn't move it twice. You were checking to make sure I was awake. Thank you. So there's a 3% chance that you managed to make this happen. Woo! That's what the world looks like when I forget my glasses. The next formula that you see is when we have a certain number of objects, but one of them is repeated, and then another one is repeated, and another one is repeated. And we do that as many times, or at least no more than the number of objects that we have available to us. Let's look at question number 3. Question number 3 wants to know what's the probability that a 7-digit phone number generated with these particular digits, 2325273, is the phone number 222-3357. Well, we want it to be this specific number, so how many outcomes are we looking for?
That's what we just gotta find out.
How many outcomes do we have that we want?
7.
That's how many digits we have.
Oh.
How many outcomes do we want? Just the one. We want this one. So our next task then is to figure out the total number of possible outcomes that we could have. How many different phone numbers are possible with this combination?
Too much.
How many items, how many objects do we have to choose from? 7 digits, because we have 7 digits in our phone number. So n is 7. Now, if we look at these numbers, we notice that we've got some repeating, don't we?
Yes.
We have this object that's repeating 3 times. So we have an R1 that repeats 3 times. And then we have this item that's repeating 2 times. So we have an R2 of 2. Putting it into our repeat formula, n factorial divided by r factorial, so on and so on. All right, plop that in your calculator. You don't have to push multiplication between the factorials. The calculator is going to assume it's multiplication. So you can literally just type 7 factorial over 3 factorial, 2 factorial. That seems like a weird number. Double check. You did 7 factorial divided by...
420.
Yeah, we got from like 3 different people. 420.
Yeah.
Did you find? Did you get it? Okay, try again. Look at what you typed and make sure that you typed it 7 factorial divided by 3 factorial, 2 factorial, and not accidentally 7 factorial over 32 factorial or something else. Okay.
Oh, I got mine wrong.
Get the decimal number, the decimal, and the percentage. Okay, what he said, and then multiply that by 100. Good job, good idea. To find out what your percentage is going to be.
Never mind.
Mm-hmm.
Oh. Get a decimal.
Yeah, you get a decimal percent,
Okay, okay.
and that's okay.
0.238095.
0.023.
0, 2, 3.
24. Around it. Yeah. So your percentages, that means it's a really, really small chance that this is going to happen. The last of the permutation formulas is the formula that lets you figure out how to arrange things in a circle where you don't have a fixed reference point. Okay? That's what happens when, say, 8 of you guys, 4 girls and 4 guys, are told, sit into a circle. Yeah, we're going to play Duck, Duck, Goose. So a group of 4 girls and 4 boys randomly seated around a table. Well, let's figure out how many different ways these 8 people, gentlemen, let's figure out how many ways these 8 people can sit. Okay? These 8 people can sit, there's 4 seats. If we look at just the girls, there's 4 ways that this first seat can be taken, yes?
Yeah.
4 different choices. And once a girl sits here, this seat now only has 3 different people that could sit there, yes? And then this seat would have 2, and then this seat would have 1. We just did a countdown thing, didn't we? Which means that the girls can be arranged in 4 factorial different ways, in 4 seats. But we want to look at what happens when we have boy, girl, boy, girl, boy, girl. Yes? So if we added in the extra seats in here for the boys, how could the boys be arranged? Well, in the first seat for boys, you have 4 boys to choose from. In the next seat, you have 3 boys to choose from. In the next seat, you have 2, and in the next seat, whoever's left gets it. Again, the boys have 4 factorial different ways
I'm
to
taking the
seat.
class here.
Yes?
Yes, ma'am.
So this is the total number of ways we can get it to be boy, girl, boy, girl, boy, girl, boy, girl. Because we don't care who's sitting next to who, right? We just want them to alternate boy, girl, boy, girl. All right, what is this number of ways that we can have boy, girl, boy, girl, boy, girl? So in your calculators type 4 factorial, 4 factorial.
5, 6, 4.
5, 7, 6.
Yes, 5 minutes.
Okay.
Yep.
The thing is we want the probability that this is the arrangement. This is just the number of ways it can be set up this way. And so really we're trying to figure out how many different ways can they be rearranged around the circle. And we don't care about the organization of them. Gentlemen, this gave us a clear organization. Now we need to figure out how much is it without a clear organization. And it's this one, the final formula that we have for permutations. How many people do we have total that we're arranging? 4 girls, 4 boys. We have 8 people. So this is 8 minus 1 factorial.
Yes.
So it's 7 factorial. How many different ways do we have to arrange these 8 people? Without caring what order they sit in. Go to your calculators, do 7 factorial. 5040, 5040. So the probability that our seating arrangement is boy, girl, boy, girl, boy, girl, boy, girl is this number of times that their seating arrangement is boy, girl, boy, girl, boy, girl, divided by the total number of ways we could arrange 4 boys and 4 girls. Find the decimal, find the percent. Yeah? I think it's going to be like 10 or 11% or something like that.
Okay.
You got what?
1, 1, 1.
1 something. Okay, you got about 11%? Right on. The permutations are definitely the most confusing of all of these to figure out. The combinations are easier because combination, order doesn't matter. And so because order doesn't matter, your formula is slightly different. So your formula looks like this. Notice how similar to permutation it looks. The only difference is we've added that repeated thing, that R, one more time. Our example reads, we have some girl named Tyron. She's won soccer trophies, 1 trophy every year for the past 15 years. So she has 15 trophies. But on her shelf, there's only room to display 9 at a time. She's going to be changing them out, and so every so often she's going to randomly put them all together in a pile and then randomly pick 9 to go on her shelf. And she's wondering, what are the chances that when I do this, I select trophies from 1st grade to 9th grade? Well, the first thing we need to do is to select the number of possible outcomes. Because order doesn't matter, she's just pulling them at random, we're going to use combination. 15 combine 9. There's the formula with the numbers put into it. That's how many different possible ways you could pull 9 trophies out of 15 trophies. Then we stop to think, how many favorable outcomes do we have? We really only have 1 shot at this. There's 1 combination that will be her 9 first years. We don't care what order they're in. We just care that it's 1, 2, 3, 4, 5, 6, 7, 8, 9 in some order. because there's only one outcome where those 9 specific trophies are chosen, our probability that these 9 are chosen is 1 out of 5,005. Yes? Okay, let's do one together so you can see it. Let's do Callie and her ice cream. Callie is my niece. She's very adorable. We take her out to an ice cream parlor because I'm deciding to be a cruel aunt to the sister-in-law. And be like, okay, Callie, I will buy you a triple scoop ice cream and then immediately send you home to your mom. There's 20 different flavors. And she's taking too long to decide, so I have her pick 3 flavors at random and that's going to be her ice cream scoop. What's the probability that when she does that, her ice cream scoop is vanilla, strawberry, chocolate? This is a combine. We have 20 different flavors, and we have 3 different things that it can be chosen for, and so we're looking at a 20 combine 3. Put that into our formula from above, and we end up with a formula that says 20 over 20 factorial over 17 factorial 3 factorial. Please, please, please don't put your factorials together like 17 plus 3 is 20 factorial. It'll break things. And don't multiply them together either. Don't do 17 times 3 factorial. This is 17 factorial times 3 factorial. Okay? So run them separate. Put them in your calculator and tell me how many different possibilities does she have if she just randomly picks 3? 1,140 different ice cream scoops that she could make some combination of these. And she's not repeating flavors, okay? So you're not going to get 2 scoops of vanilla and 1 scoop of something else. Now, the odds that she chooses vanilla, chocolate, strawberry, because we're not allowing repeats, is that this only happens once. And so that's her probability. Put it as a decimal, put it as a percent, call it a day. Sound good?
Yes, ma'am.
All right. Oh my goodness, where did all my papers go? Next up is going to be geometric probability, which is 13.3. I don't know where my blank one went. This is so weird. All right, so 13.3 oh, here it is. 13.3 is what's called geometric probability. It's the same probability that we've been dealing with. It's this fraction of the number of thing we're looking for divided by the total number of things possible. Except this time we're going to use geometric measurements to help us out. Lengths, areas, volumes. No, we're not doing volumes. We're only doing length and we're only doing area. So let's say we have this line segment ZP. And we're going to pretend that it's a dartboard, but it's a magic dartboard that whenever I throw a point at it, it's always going to hit this line. But it's random as to where this point is because I'm not very good at this game. So we want to know the probability that M is on the line segment piece from Z to Q. We're going to find the length of ZQ and divide it by the length of ZP, and that will give me the probability that I hit the line somewhere on Z through Q. What's the measurement of ZQ? Guys?
2.
2. And what's the measurement of ZP?
10.
10. You added them all up. Beautiful. Reduce that fraction to lowest terms. Put it as a decimal. Put that decimal as a percent. And call it done. Easy peasy? Good. Let's look at number 5 because number 5 is probably the weird looking one. Because it's talking about a traffic light and your knee-jerk reaction is, but miss, we can't put a ruler up against time. But here's the thing we already have. Some of you are already counting the minutes, by the way, there's 23 of them, until we leave today. You have put a ruler on time. This amount of time is 1 minute. And so we can think of this 5-minute traffic cycle as a segment of your life that you were watching this traffic signal. And it's going to take 5 minutes from when it starts to turn green until the next time it turns green. Now, in this 5-minute cycle, it spends 2 minutes and 27 seconds of it green. Then it spends 6 seconds of it yellow. And then it spends 2 minutes, 27 seconds of it red. And the question is, what is the probability that when you're driving and you get to this specific light, it's green? Really, in terms of our probability, they want to know how long is the green segment of time in relationship to the total segment of time that this thing spends going through its cycle. It's green for 2 minutes, 27 seconds out of the grand total of 5 minutes that it is running. We can't put this into decimal format because they're in 2 different units of time. We have minutes and we have seconds happening at the same time. So we need to convert this minute seconds into a single unit of time. Either everything in minutes or everything in seconds. Which do you want to do?
Everything in seconds.
Everything in seconds. All right. You could have done everything in minutes. That would have been fine too. Let's do his suggestion. Do everything in seconds. How many seconds in 1 minute?
60.
So if you have 2 minutes, how many seconds do you have?
120 seconds.
120. And I have 27 more seconds. So 120 plus 1.
147.
Yes, that. I got tongue tied. How many seconds in 5 minutes? 300 seconds in 5 minutes. And now we're able to divide and figure out our probability that if we go up to this particular light, it's going to be green. Yes?
What's that number?
I don't know. What's your calculator say? Do 147 divided by 300. Oh, it's a 300. Oh, that was the number you were asking me for. Sorry. Yeah, that means 300. These characters here, that's S for seconds. Okay? At a guess, you're going to get something close to about a half. 49? So 0.49 or 49%. Okay. We rounded. You may have gotten something slightly different because of rounding. That's okay. Turn the page and you will see that you can also do this for area. You are very good with area. Areas of triangles, areas of circles, areas of squares, areas of trapezoids, areas of triangles. I already said triangles. You're also good at finding the areas of shaded portions. So this, since you want the area of the shaded portion, your probabilities are going to be the area of the shaded portion divided by the area total. Make sure you give it in decimal and percent. Okay? I don't feel that I need to go over this one? No? You feeling pretty good on the areas? Okay. This is the one I want to spend some time on, and we're doing really good. We have 20 minutes, and we only have 3 sections left. Thank you so much for your endurance today. I know this has been difficult. Very tiring, yes. The next section is about simulations. Now, my father tried to do a simulation of the Texas lottery so that he could figure out how many tickets he needed to buy so that he can win the big jackpot. Yeah, he realized very quickly this was going to be too much for him, and he quit about halfway through. But he was a number nerd, and so he started doing it for fun. But these were the steps he took. He determined the possible outcome. He wanted to know what it would take to match 3, match 4, match 5, and match 6. And then he went online and he found the theoretical probability of doing just that. They have it on the Texas Lotto website, by the way, if you're wondering. Then he stated any assumption that he had to make. He described what probability model, that is the mathematical model that is going to match something that happens randomly. He was working on building that also. And then he defined what trial he was going to use to see how many times he had to run this before he actually got the match that he wanted. And then he was going to state the number of trials he was going to do. So let's look at this example here with Joni, and then we'll write one together, you and I. So Joni, baseball player, last season got on base 40% of the time she was up at bat. We need to design a simulation to determine the probability that she's going to get on base at her next time on bat this season using her last season's stats. Here's the paragraph that explains the simulation that they've designed. The possible outcomes are that Joni gets on base, 40%, and that she doesn't get on base, 60%. Assume that Joni will have 90 at-bats this season. She'll be up to swing 90 times. Use a spinner. Here's the model that we're using. We're going to use a spinner that's a round circle thing with an arm, and you go, and it spins, and then it stops and lands on a section. One of the areas contains 40% of the total spinner area. That is, the central angle for that section is 144 degrees. They got that degree measured this way. An entire circle is 360 degrees. Multiplied by the 40% as a decimal, 0.4, and the central angle is 144 degrees. Okay, so that's how they got that. The other section is 60% or 216 degrees on that central angle. Then we're going to describe the trial. One trial is one spin of the spinner, and that's going to represent Joni going up to swing at the ball one time. Not she has one swing, but she has one attempt to try to get on base. So she could strike out, or she could hit a home run, or she could hit a double or foul or something. She could do something in there, but what we're actually looking for is her on base or her not on base. Okay, make sense? Okay. A successful trial is she got on base, and a failed trial is she did not get on base. And the simulation is going to have 90 trials because we're assuming she's going to have 90 chances this coming season. Okay, do you see how we made that simulation happen? Let's make a simulation together. Let's do the movie rentals, number 3 at the very bottom, and I'm going to fold my page so that way we can see the example and then the question we're going to do together. Because what we're going to do is we're going to take the answer they've given us and copy the pieces that we need and just change the information so it matches what's in front of us. Okay? And that's what I'm going to suggest you do for all these simulations. Copy the format that they have and change just what you need to change to make it fit the situation that you have in front of you. A local store has 5 videos in its fairy tale section. Last month, Cinderella was rented 35% of the time, Snow White 30, Sleeping Beauty 20, Rumpelstiltskin 10, and Rapunzel 5. No love for Tangled. They didn't tell us what kind of simulation to run, so what simulation do you want to run?
What do you mean?
See, on the example, it told us to design a simulation to determine the probability she'll be on base. And number 3, it doesn't give us what simulation we want to run, so we have to come up with that. What kind of simulation do we want to design? What are the possibilities? Well, we could have a simulation that states how many times a particular movie was rented over any others, or just a simulation to tell us how many times each movie was rented. Which simulation would you like to have? The first one. Okay, so we're going to design a simulation that tells us which movie. Pick one. Cinderella. So design a simulation that says the probability Cinderella is rented. And we'll say this month because the data that we have is for last month. All right, we now know what kind of simulation we're designing. We can start designing it. What are our possible outcomes? Well, if we're concerned that Cinderella is rented our possible outcomes are Cinderella's rented or Cinderella's not rented, right? So those are our two outcomes. All right, so the possible outcomes are, and for your answers, you'll need to write all of this down. The possible outcomes are Cinderella is rented. And what's our theoretical probability for Cinderella being rented? 35%. Our other outcome is that Cinderella is not rented. What's the probability that Cinderella is not rented? 65%. How did you get 65%?
Percent goes to 100, so I should have to do that.
Because percents go up to 100, and so if we already used 35 of it for it to be rented, then the other remaining percentages it didn't get rented. Very good. What's our assumption? Now here it said, in our baseball example, that Joni was going to be up to bat 90 times. Since we're talking about movie rentals, we should assume that the movies are rented some number of times. How many movies are rented? Make up a number.
15.
15. Assume that 15 movies are rented. Let's use the spinner technique, because that's what we have here, yes? So use a spinner divided into, how many sections are we going to divide this into? Well, how many possible outcomes do we have? 2. We've listed 2. We've listed the rental of Cinderella and the rental of something not Cinderella. So we're going to divide this into 2 sectors. One sector will contain 35% of the spinner's area. Or we're going to give it a central angle of, go to your calculator, and find the central angle that is 35% of a full circle. 360 times 0.35.
So 126.
126. So if we give our spinner a central angle of 126 degrees, we'll have that sector being 35% of the entire area of the spinner. And then the other area, other sector, is 65%, we're on number 3. The other sector will be 65% of the area, and you'll find the angle measure for that. All right. Then we need to define what a trial is according to this paragraph.
That's our big.
So a trial, which will be one spin of our spinner, will represent what? In our example, it represented one time that Joni was at bat. In this example, we're talking about movie rentals. So one trial should represent what? Yeah, one movie that got rented. One movie rental. A successful trial is Cinderella was rented. A failed trial is Cinderella was not rented. The simulation should contain, not 90. How many trials? Well, how many movies did we assume got rented? That's how many trials you should have. Make sense on how we write that out?
Yeah.
Okay. We have 8 minutes for 2 sections. I know we can do it. Thank you.
You're welcome.
All right, we're looking at the idea of independent and dependent events. These are events that independent, they have nothing to do with each other, and dependent events meaning that one has to happen before the other one can happen. Okay?
So like, for instance,
Huh?
like when we were going over the assignments with classes.
Yeah, like when we were going over the textbooks in the locker. All right, so if it's an independent event, let's look at number 1. Number 1 says the king is drawn from a deck of 52 cards. So we're drawing cards from a deck. And then a coin is tossed into the air. Could the act of me drawing a card from a deck possibly affect what's going to happen when I flip a coin?
No.
No, these two things aren't related to each other. And so they're independent events. And so we're going to write the independent probability this way. The probability that we draw a king is 4 kings out of the 52 cards. The probability that we get heads is 1 head out of the 2 sides of the coin. And so the probability that we have a king and a head on a coin is the probability of the king times the probability of the head on the coin. Turn it into a decimal, turn it into a percent. And this was an independent event. Make sense? Let's look at number 3. Number 3 has marbles in a bag. So we have a red marble drawn from a bag that has 2 blue and 5 red marbles. How many marbles do we have in the bag total? I know you guys are real tired. Bear with me. Give me 6 minutes. 6 minutes. How many bags are in the marble total? How many marbles are in the bag total?
7.
7. 4 blue, 5 red. If I draw a red marble, what's the probability that I've drawn a red marble?
4 to 7.
How many do I have to start with?
5.
5. So 5 of 7. Now, it's not replaced, which means after I do that first drawing, the number of marbles, of red marbles, goes down by 1. And so if I were to reach in and draw another red marble, what would be my probability?
4 to 6.
4 out of 6, because now I have 4 red marbles and 6 marbles total. So the probability of drawing a second red marble is 4 of 6. Make sense? All right. Same sort of thing happens on the back sides of the page, so there's just some more for you to work with. Let's look at our very last section. We have 5 minutes. You guys are doing amazing. Give me 5 minutes or less.
You need to give us 5 minutes or less.
5 minutes or less. Ready? Okay. We're talking about the mutually exclusive or non-mutually exclusive events. These were always hard for me to understand, like which one is which, and so here's the best way I can think of to explain it. A mutually exclusive event would be something like this. Going to the animal shelter to adopt a pet, wanting a cat or a dog, and picking an animal at random. There's no way for this animal to be both a cat and a dog at the same time. Even if it's a cat that thinks it's a dog, because it comes when you call, it sits when you tell it, it shakes paws, it fetches candy, like, it's still a cat. It just thinks it's a dog, okay? We're not dealing with cats that identify as dogs. It's just a cat, okay? Whereas with this one, when we're rolling dice in a game, assuming this dice has 6 sides, it is possible for us to roll a 6 and an even number at the same time, because 6 is an even number. Does that make sense? So if the things cannot happen at the same time, it's mutually exclusive. And if they can happen at the same time, it's not mutually exclusive. Once you've determined that, you will use one of these two formulas in order to help you find the overall probability of these two events happening at the same time. Okay? Yes? Flip on the back. And the last item in the 3 minutes we have left, you guys are amazing, is the probability of complements. A complement is everything that isn't what you wanted to have happened. So if we go back to the pet store idea, if I went into the pet store and I wanted to select a pet, I wanted a cat. The complement of the probability of me selecting a cat is the probability that I'd select anything but the cat. This one, number one, is the probability of something that will always happen. If I go into a pet store to select a pet, I am going to select some sort of animal. I'm not going to walk into the pet store and have selected a rock. I may have selected an animal that looks like a rock, turtle, but I will not have selected an actual rock. It will be some sort of animal, right? So the one probability is saying, dude, you're selecting an animal. And this probability is the probability of me selecting the animal that I wanted, which when I subtract them will give me the probability of me selecting the thing I didn't want. Make sense?
Yes.
All right. Thank you guys so very, very much.